Now that we know about all the properties of the Laplace transform, why they work, how they work, we can actually apply it finally to solving a differential equation. So let's try to solve the following differential equation. Y double prime minus 2y prime plus 5y equals 0 with the initial conditions that y of 0 equals 2 and that y prime evaluated at 0 is equal to 4. Now, the way that you solve a differential equation, specifically an initial value problem with the Laplace transform, is that you try, it's 3 steps. Step 1 is that you take, I guess I'll write it over here. Step 1 is take Laplace transform of both sides. So what you're doing is you say Laplace transform of the left side, Laplace transform of the right side, and you're going to try to isolate, based on the property of derivatives, you're going to try to isolate the Laplace transform of y, which is your solution. Once you've isolated the Laplace transform of your solution, your third step is to take the inverse Laplace transform of whatever's on the right-hand side. And then that will equal the inverse Laplace transform of the Laplace transform of y, which is just y. These are the 3 steps we're going to go through for the solution. Another very important thing to note, so this is like important note, is that the Laplace transform only solves initial value problems. It only solves initial value problems. The reason that it only solves this type of problem is because of the way that the Laplace transform works with derivatives. So if you remember, if we take the Laplace transform of a derivative, f prime of t, it's going to equal s times the Laplace transform of f of t, which is big F, which is s, minus f, regular f evaluated at 0, and then the Laplace transform of a second derivative, and we created a formula even for the nth derivative, but in this case we'll just do it by hand, is s squared f of s minus f evaluated at 0 times s, minus f prime evaluated at 0. So it might be clearer now that the reason that it only solves initial value problems is because initial value problems are the only cases where we're going to get initial conditions at 0, so that we're going to be able to say, oh, f prime at 0 is 4 type of thing, which in our case is actually true. Y prime at 0 is 4. So this is why the Laplace transform only solves initial value problems. Hey, luckily we have an initial value problem, so let's get cracking. The first step is to take the Laplace transform of both sides. So the Laplace transform of the right side, if we remember, we can break it apart by addition, because the sum of the Laplace transform is Laplace transform of the sums. That's linearity. So the Laplace transform of y double prime, factor out the 2 minus 2 times the Laplace transform of y prime, plus 5 times the Laplace transform of y itself, is going to equal the Laplace transform of 0. Now, the Laplace transform of 0 is equal to 0, and although we haven't formally proven it's very easy, the 0 gets multiplied into the integral, and the integral of any bound of just 0 is 0. So, now we can apply our derivative formulas. So, the Laplace transform of y double prime, we're going to use this guy right here. Laplace transform of a function's second derivative equals s squared times that function's Laplace transform, which I'm going to write as big Y now to save some space, minus s times that function evaluated at 0, minus the derivative of that function evaluated at 0. Now we subtract 2 times the Laplace transform of y prime, which is s times the Laplace transform of y, minus y evaluated at 0. And now we have plus 5 times, well, just the Laplace transform of y is big Y, all equaling 0. Alright, remember, this is all separate here. This is separate from the actual differential equation. Alright, I guess we'll even finish it off this way. Great. Now we have something looks like this. And what we can do is try to do step 2. Isolate the Laplace transform of y. And what we see is we have these different Laplace transform of y terms, and then we have other non-Laplace transform of y terms. So first, let's look at just these terms with the big Y in them. What we're going to get if we take them away separately is that the Laplace transform of y times, and then s squared, and then here minus 2 times s, and then here plus 5. All of that times the Laplace transform of y. And notice also this polynomial is the same as up here, and you can show why that's true. It's kind of cool. This times the Laplace transform of y minus s times y of 0. But we know what y of 0 is. We're given it as an initial condition. Y of 0 equals 2. So this is minus 2s. Minus y prime of 0 is minus 4. And then minus 2 times y of 0. But minus y of 0, so minus 2. And then this all equals 0 because we already took out this 5 and put it in here. And what we're left with is negative 4 minus 2 times negative 2 is plus 4. So negative 4 and plus 4, these guys annihilate each other. And then if we add 2s to both sides, then we get that this equals 2s. Now we can just divide by s squared minus 2s plus 5, and we'll get an expression for the Laplace transform of y. Namely, Laplace transform of our solution, y of t, is precisely equal to 2s divided by s squared minus 2s plus 5. All right, now if we take the inverse Laplace transform of both sides, we get that our solution is the inverse Laplace transform of any Laplace transform is just the function. So our function, our solution, y of t, is equal to the inverse Laplace transform of 2s divided by s squared minus 2s plus 5. Fantastic. Now, this would be a point that might be a wall for some people, and it was for me, because I didn't really know how to deal with this at first. So the trouble spot happens when you notice, okay, this isn't of any form of the Laplace transform we know, first off, so we can't just use a formula that we already know. All right, let's factor it. No factors. And we can prove that because the discriminant, which is b squared minus 4a, is 4 minus, and then we have minus 4a, so 20. So 4 minus 20, this is negative 16, which means we will have two complex factors. That's not very nice to work with, and I bet the partial fraction decomposition would be horrendous. And there's really no other way we could go about doing this, except that there's a way of thinking about this that lends itself very nicely to this type of inverse Laplace transform, and that is completing the square. What happens if we complete the square here? What we get is the inverse Laplace transform of 2s, and let me maintain my colors here, of 2s divided by, and when I say complete the square, I mean try to get this s and then minus 2s all together. And we do that by noticing, well, hey, s squared minus 2s plus 5. It's not a perfect square, but it's kind of close. We could say s minus 1 squared. That, in of itself, gets us the s squared term, and it gets us the negative 2s term. It also gets us a plus 1 term, so if we just add 4 to this, they're equal, right? So we can say equals s minus 1 squared plus 4. All right, fantastic. Well, what are we going to do with this now? Okay, well, it actually is coming together. Let's factor out this 2. So we're going to get 2 times the inverse Laplace transform of s divided by s minus 1 squared plus 4. Is this ringing any bells? Forget about this minus 1 for a second. S over s squared plus some kind of perfect square. That, to me, screams cosine. Specifically, the cosine of 2t, because we have 2 squared equals 4 here. So this is what it's screaming to me, is cosine of 2t. There's just one problem. This minus 1. How are we going to fix that minus 1? The easiest answer that, I mean, it's kind of clever, it might just pop out of you, is, well, hey, we could multiply this by an exponent, because didn't you say that the Laplace transform of an exponent, let's say e to the 1t times the cosine of 2t, wouldn't this be equal to, precisely equal to, s minus 1 over s minus 1 squared plus 4? You'd be right, it's what it's equal to. This is the Laplace transform of this, because it's the Laplace transform of cosine of 2t shifted by negative 1. Well, shifted by positive 1 in the negative direction, e to the t. And the only thing we run into now is, unfortunately, we don't have an s minus 1 on top. But sneaky as us mathematicians are, we can get around this dilemma too by adding and subtracting 1. So, I know, we're getting pretty crazy here. What I claim to you is that, again, our solution, y of t, which now, going off of this form, is equaling 2 times the inverse Laplace transform of s divided by s minus 1 squared plus 2 squared, I'll write it, that this is the same thing as 2 times the inverse Laplace transform of s minus 1 plus 1, so we haven't changed anything, all divided by s minus 1 squared plus 2 squared. But now linearity saves us, because we can take this s minus 1, make it its own Laplace transform. Take this plus 1, make it its own Laplace transform. So what are we left with? We're left with this equaling 2 times the inverse Laplace transform of something we know how to take, s minus 1 divided by s minus 1 squared plus 4. Plus, and you'll see why in a second, the inverse Laplace transform is taking the 2 in, of 2 over s minus 1 squared plus 2 squared. Boom. Now we know how to take the inverse Laplace transform of each of these components. What we get is that this means that now, here's solution y of t. So inverse Laplace transform, first of all, 2 times, what is the inverse Laplace transform of s minus 1 times divided by s minus 1 squared plus 4? Well, we've realized that's just screaming cosine of 2t. In fact, because of the shift of exactly 1 on both s's, it's e to the t cosine of 2t. So this is 2 times e to the t times the cosine of 2t. And now we're going to add to this the inverse Laplace transform, 2 over s minus 1 squared plus 2 squared. This, to me, this is screaming the sine of 2t, because we got a 2 on top, and we have a 2 squared on the bottom. The only issue is we're getting shifted by 1 again. So we could just say this is e to the t sine t. And that's it. Now we can go back and say this is plus e to the t times the sine of t. And this is our final answer. You could remove the parentheses, but you don't even have to. We're done. This is the solution to the differential equation. And if you wanted to, you could check it. One thing you could do, for example, is oh wow, I wrote t. This should be 2t, because 2t over there, sine of 2t. If you wanted to, we could actually simplify this a bit. So okay, before I go into my green here, let's just simplify this one more step down. We say our solution, we can factor out an e to the t, is e to the t times 2 cosine of 2t plus 1 times the sine of 2t. Interesting. Maybe now this is looking quite a bit like the form for perhaps a complex root of a homogeneous equation. That would be absolutely correct, because if you remember, our differential equation itself was y double prime minus 2y prime plus 5y equals 0. If we found the roots of this, which we actually did, it would be the roots are negative b, so negative 2 is plus 2, plus or minus the square root of 4, which is negative 2 squared, minus 20, which is 5 times 4, all over 2, which is 1 plus or minus, and then this is going to become negative 16, so I times the root 16 is 4 over 2 is times 2. These are our two roots. Interesting. We're seeing this 2i pop up here as 2t, as the how quickly the sine and cosine are oscillating. We're seeing the 1 pop up in the t here as how quickly it is decaying or growing. And we see that we have our two constants, 2 and 1, that must have somehow popped out of our initial conditions. It all lines up. In the next video, I'm going to do another Laplace transform, maybe even the next series of videos, because this is definitely one of the topics in differential equations, how to actually solve a differential equation with the Laplace transform that is just good to drill on a lot. So I would recommend also, if you want to just get out pen and paper, you can look up differential equations to solve. You can make up your own differential equation to solve with the Laplace transform. Just give it a go. It's kind of fun. See you in the next video.